Welcome back, everyone. So let's look at solutions. Just a quick sort of overview about what you know about solutions. So particularly saturation of solutions. So let's remind ourselves we know about a solution means that you've got a solvent, right? And you put in usually some sort of solid particles, right? Some sort of solid particles that a substance of some type, usually an ionic compound, and then that's your solute, right? And then all of this together is your solution. All right. So what we're interested in deals with saturation of solutions. So with that, what we want to think about is your favorite thing, which is math. So we need a graph. Okay. We need ourselves a graph, or at least the concept of a graph, right? So when you have a solution, typically you have some sort of change in temperature, all right, and that's usually in degrees Celsius. That's usually the unit, all right, and then you have X amount of solute, and typically we'll just kind of call it right now. We'll just say grams. Typically measure that in grams because we're going to be measuring in small scale. If you're in manufacturing, of course, you would. These are the industry standards, and you take it to a larger scale, and you would do conversions into kilograms and stuff like that. But grams is basically where we're focusing on, right? And so there is this concept of what's called a solubility curve. Okay. I can't even spell. Solubility curve. So you've learned from math class, a curve. If you've got some sort of regression line on a graph, you call it a curve. Even if it's a straight line, it's called a curve, right? So right here, this implies some sort of linear relationship, where because you see that how that curve goes up, or even if it went down in this way or whatever. I mean, this particular type of graph implies some sort of linear relationship. And, in your basic math classes, you learn how to write equations for these lines, right? So, but for us in chemistry, what we like to focus on is a couple of things when it comes to saturation. So, what's important for us is below, above, and on the line. So, at any given temperature, so I'm just going to pick this spot right here, okay? Just arbitrarily picked it. What we're saying is if I had this amount, if I had X amount of solute at this temperature, then I would have a saturated solution. I would have a saturated solution. What that means is at that temperature, there's the maximum amount of solute in that amount of water that I can have. And we're going to look at that here very shortly, some very specific. But this is just a basic concept. So anywhere along this curve, anywhere along this line here, at any given point, it could be this point, it could be this point, it could be this point. It doesn't really matter. If when you're looking at the temperature and the amount of solute that is in solution, and it is exactly on that curve, then you are at the saturation point. All right, so it's a saturated solution, so we would say that's the saturation point. All right, if you happen to be below this, right? If you are say, it would say you were at this same temperature here, but you only have this much salt. Well, if we come over here, all right, this right here is less than X amount of salt, right? We would say that this is unsaturated. We would say we would have an unsaturated solution. And what that means is that there's all of this right here. If we look at the difference right there, if we mathematically look at the difference right there, that's the same thing. Because remember, in math class, you can move your lines parallel, and it's still the same value. I don't care if you're talking about parallel, left to right or up and down. It's still the same. It's still the same value. So what we're saying is whatever this is here, here's x. This is less than x. Whatever the difference is, right there, at this temperature, it could still hold that much more. It could still hold that much more of the solute, whatever solute it happens to be. All right. And then we've got, let's just say we're still at the same temperature. Okay. So at the same temperature, and we go up, we go up, we go up, we go up, and then we're right here, right? So this right here is not x, this is a greater amount than whatever x is, right? And so you can see that right there, all right, come parallel to that, whatever that value is, that is that much more. At this temperature, it can only hold this much until it's completely saturated. What that means is for the amount of water molecules that are there, the water molecules themselves cannot hold on and keep dissociated the ions that are in that solution, that are dissolved in that solution, or the particles that are kept separate in that solution, like say for instance sugar molecules, right? If we're talking about salts, and we're talking about the ions that are separated, the cations and anions that are separated according to the polar and non-polar parts of the water, right? Positive, negative. So what we're saying is right here that this is above the saturation point, and the term for that, what we would say is that this is supersaturated. Super is a prefix that means above something else, greater than something else. If you have a super amount, it's above that, right? Sub, under, super, above. And that's really the basics of that. You don't need specific numbers, it's just a concept. So when we do look at a graph that has specific solutes and specific temperatures, we can get specific amounts, and then we can actually look at this. This is something that we will be doing in lab, and where you actually heat up various concentrations of solutes, and then as you take a look at certain amounts at different temperatures, you can look at the heated and cooling of it going up and down, plot points on a graph, just like your math teachers taught you, and then we just basically have our own little curve that we could follow, and we can extrapolate some information from that. So let's go ahead and let's practice. Let's practice that a little bit. All right, let's practice this graph right here. So let's go down here. I just went online and found this graph. All right, this looks like a good one for us to. I mean, it's got some nice colors on it. It's a typical graph. There's a bunch of different ones. Sometimes you'll find these where it's just an explosion of different curves. So there's multiple curves on this graph, and your math teachers have taught you how to look at graphs that have multiple pieces of data. Sometimes you usually do just like 2 or 3 in one graph. So here there just happens to be a whole lot. So these are referred to as solubility curve and curves, and what you're doing is just these are known standards. So this has been meticulously looked at in laboratory situations, and so these are the standards that we follow, and we can use these as guidelines if we're wanting to do experimentation, whatever the case might be, with different compounds at different temperatures. If we know these standards, then we'll know how much solute we can actually get into those solutions. All right, speaking of solution, caffeine solution. All right, let's take a look. So first thing I want you to really pay attention to is, see, there's temperature on the bottom, and degrees Celsius is our unit. And then solubility, and notice it says grams of salt. And then there's a little extra added thing here where it says grams of salt that is in 100 grams of water. So the first thing that you really need to try to remember is that 1 gram of water is equal to 1 milliliter of water. And remember that it comes from the basic concept of the basic thing about density of water. So the density of water, it was like 0.998 and several other numbers, right? Grams per milliliter, per cubic centimeter, right? And so it's a 1-to-1 ratio. So if you have 1 gram, you have 1 milliliter of water. So keep that in mind, all right? But the reason why grams of water is used instead of saying milliliters of water has to do with the fact that there are things in chemistry where certain properties of things change, but the mass of what you're looking at doesn't change, even though a certain property might change. And that's a lesson for something else later on. But just know that there are times when just understanding the concentration of a solution it's important, but what's more important is to understand the mass of solvent that you're working with, because that mass of solvent doesn't change no matter how much you heat it up, so long as you keep all of the solvent captured. If you don't reach its boiling point and then it escapes as vapor, so long as you can keep that contained, then you have all the mass of that solvent. So that's the reason for this here. All right. For our purposes on this, we just need to keep in mind 1 gram of water, 1 milliliter of water. It's a 1-to-1 ratio, right? All right. So let's take a look at this. This says how many grams of calcium chloride can be dissolved in 100 milliliters of water at 10 degrees Celsius. All right. So we're at 10 degrees Celsius. We've got to find calcium chloride. That's this one right here. So 10 degrees Celsius, we go up. We just follow this. We go follow this at 10 degrees Celsius. And so that brings us to about right there, right? That brings us to about that point right there. So it says how many grams of calcium chloride can be dissolved in 100 milliliters of water at 10 degrees Celsius? Well, at 10 degrees Celsius, so 65 would be that midway point right there, right? Because there's 60, there's 70, there'd be 65. So there's a pretty solid argument here that this is approximately 62 grams. It looks that the halfway point kind of being right there, 62, 63, 64, 65. So I just kind of counted up from this point up to that midway point. So we're looking at about 62. There might be an argument to say 63, but it looks a little bit on the lower side of that curve, closer. It looks like it's closer to this point here than it is the midway point. So approximately 62 grams. In reality, it's it could be something like 62.4, 62.6, something like that. All right. But what we're looking right here is just looking for a good rounded estimate. So on a quiz or a test, 62, 63 would be acceptable. Any more than 63 would be unacceptable, or any less than 62, because you're just not reading the graph correctly. And your math teachers have taught you how to do this, so try to be as precise as possible. Okay. So now we've got what's potassium dichromate. That's that compound right there. How many grams of potassium dichromate can dissolve in 100 milliliters of water at 80 degrees Celsius? All right, so 80 degrees Celsius. So we just ignore all the other curves. All we're worried about is this curve right there. This purple line here, this pretty purple line of potassium dichromate. So 80 degrees Celsius. We go right there. And so there's the 60 mark right there. We have to get this one right here, right? So there's 50, there's 60. So there's a pretty good argument there for that's approximately 58 grams. It looks like we have about one more tick mark between there and the 60 mark. 58 would be a really, really good guess. There's not much room for error on this one. This one's pretty straightforward. I would say 58. You know, of course, in reality, it could be 58.2, might be 57.85. You know, if you have really good, accurate measurements. For our purposes, 58 is going to work great on this. Hopefully, you can see that. And then let's see the third one. We've got how many grams of lead to nitrate. All right, lead to nitrate right here. So you're just worried about this curve. All the other ones, ignore them. So now one of the first things you see is lead to nitrate. You see how it's got that very nice steady increase. And so some do that. So you'll notice lead to nitrate. Look at the potassium chloride on this, sodium chloride. Notice in the sodium nitrate, notice you do get some extremely linear relationships. I mean, the lines are like almost, I mean, they're perfectly straight. And that happens with certain types. You know, you'll notice that the two nitrate compounds on here, two of the nitrate compounds, sodium and the lead 2, have that. The potassium, notice it's not quite like that. It starts off a little more like a lazy S, and then it almost looks like an exponential increase. I mean, it's a pretty sharp increase. There'd be ways we could mathematically analyze that to see exactly what the relationship is, but we just know it's a curve. That's all we need to worry about right now. So lead to nitrate can be all right. So we've got at 40. Let's see, at 40 degrees, right? Let me underline that a little better for you. 40 degrees. So let's find our 40 degree mark. We go up, 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 we go up. That puts us right there at that point right there, right? And so that looks like it's between 70 and 80. So that we would say 75 grams. But if you wrote 75 grams, you would be wrong. So let's think about this for a second. Why would we be wrong? And if you've already noticed this ahead of time, good for you. If you haven't, let's reread the question and let's think about this. This unit here says for every 100 grams of water. The problem says we have 50 milliliters of water. 50 milliliters is half that volume, which means we can only hold, or this particular solution can only hold half of that mass, right? And so half of that mass is 37.5 grams, right? 37.5 grams. So if this problem said how many grams of lead 2 nitrate can be dissolved in 200 milliliters of water, so we went back up here, we would have seen 75, but remember that's 75 grams in 100 milliliters of water, right? 100 grams of water. So if we have twice that volume, we would have twice the amount of solute. So it's almost like thinking like you've got one beaker here with 100 milliliters that holds 75. You have another beaker with 100 milliliters of water that holds 75. If you pour them both together into one, you have 200 milliliters, and you would have 150 grams of salt in one container. All right. And then the last part, it says 40 grams of potassium chlorate is added to water that has been heated to 90 degrees Celsius. All right, so our potassium chlorate, this compound here, 90 degrees. We're going up, we're going up, we're going up. It says 40 grams, right? At 90 degrees, 40 grams has been added in. Well, you notice 40 grams right here. It doesn't. 40 grams of your potassium chlorate. That we actually at 90 degrees, we actually could have added up to about 46, 47. So if it was only 40 grams, if you think about it for a second, how do we have a supersaturated, saturated, or unsaturated solution? I'll give you a moment to think. And if you said unsaturated, you'd be correct. So right now we have an unsaturated solution. Okay? We have an unsaturated solution. So we have 40 grams in there when it could hold about 46, 47, right? Probably more like 47. Or 46. So now it says it cools down to 75 degrees, right? So 75 degrees, halfway, we're right there. All right, so on that line, so that looks like we're between the 30 and 40 mark. So at this point, if at 75 we're right here, remember this is the saturation point, and that value there looks to be 35 grams in 100 milliliters of water. And in this problem here, we're assuming we have 100 milliliters of water because it doesn't tell us we do, it doesn't tell us we don't, so we have to assume we do. All right. We initially added 40 grams at the 90 degrees Celsius. And then it was allowed to cool down, right? And then it cooled to 75 degrees Celsius. Well, if we start off with 40, and if the saturation point is 35, then the difference has to be 5 grams. So 5 grams at 75 degrees, that would be how much we precipitate out. All right. So the solution at 75 degrees can only hold 35. But you had added in 40. So when it was at a higher temperature, all of that could dissolve. That wasn't a problem. But now that it's cooled down, there's less molecular motion, less volume of water, and so the max amount of solute, as we see at that saturation point, is 35. So the other 5 grams literally falls out of solution, and you would see it precipitate out, and you would see the particles settle at the bottom. But you'd have to begin to heat it back up so that you could. All right, so that you could do that. So let's think about this. So there's 40. So we have to get to that temperature right there. So if we follow that down, then we're at 75 right here with 40 degrees. So I'm just extending this a little bit further. So if you think about it, according to this, we would have to heat it up about another 7 degrees Celsius to around 82 degrees Celsius, and all 40 grams would dissolve. So then those other 5 would then dissolve back into solution. Okay. All right. Hope this helps. Pause, rewind. I will leave timestamps down in the comments so that you can easily get back and forth to the first part of the video where we looked at the basics, and then to various parts of this right here as well. So hope this helped. Study hard and work on those problem sets. Be sure to ask me questions, send me some comments if you need any help. Take care.